In this video, to start with, we're going to see how a reaction is going to proceed. Is it going to go towards products or towards reactants? Here we have one of the steps in iron purification, where iron oxide solid has carbon monoxide blown over it. This can react to strip the oxygen off of the iron, making iron solid and carbon dioxide gas. This has a Kp of 0.259 at 1000 Kelvin. Well, this is running through, and they're testing the outflow gas as the gas moves through the reaction chamber. And the outflow shows that there's 113 torr of CO2 and 560 torr of CO. What we want to know is, how will this reaction proceed? Towards products or towards reactants? Have we successfully finished reaching equilibrium, or are we not yet there? In this case, we have to set up our Q expression. Well, it's going to be products over reactants. I have CO2 gas, iron solid, which solids will get canceled out. Iron oxide solid, that'll get ignored. It'll get canceled out as well. And CO gas. So really, I just have the two gases to worry about, which makes sense. I have a Kp, I have a K for pressure, and a bunch of pressure readings. So the solids aren't part of our expression, but my product is going to be the pressure of CO2 to the first power divided by the pressure of CO to the first power. CO2 was 113. CO was 560. Remember that technically we use our activities here in our Q values, so these pressures would be divided by the standard state, so they've lost their units. 113 divided by 560, we'll find a Q value of 0.2018. Well, that means our Q is presently less than our Kp. So 0.20 is less than 0.26. This means I don't have enough products. I have too much reactants. I don't have enough on top when I do my division. That would give me a larger value if I had more on top. So this has not yet reached equilibrium. If we had a sealed reaction container and it had some iron oxide on the bottom, and we pumped some CO in, as they bounce off, steal that O and become CO2, we have not yet reached equilibrium, and we'll still remove more oxygen from that iron oxide if we allow this reaction to continue this way. So this is still proceeding towards products. It hasn't reached the most products it can make yet. Well, brings up question B then. When will it stop? When will it be at equilibrium? Specifically, what will the pressures be? How do we know when it's at equilibrium in this case? For that, we need to employ an ICE table. ICE tables start with the initial concentrations. They observe the change that occurs and identifies what the concentrations will be at equilibrium. So initial, change, and equilibrium. We've really only got the two chemicals we're concerned about, CO gas and the equilibrium that leads to CO2 gas. The irons are in there, but their concentrations are ignored. Initially, I'm concerned about the irons, and we had 560 torr worth of CO and 113 torr worth of CO2. There's going to be some change. Sometimes just a little delta symbol here for it. I'm concerned with our iron species as their concentrations aren't altering, but carbon monoxide, well, if we're still proceeding towards products, we're going to use up starting material. So I must lose some amount of my starting material. Since I'm proceeding towards products, I must make some amount of product. Well, for every one CO that gets used up, it makes one CO2 just from the balance reaction. So whatever number of CO, carbon monoxides, goes away, I must produce the same number of carbon dioxide. If I'd had a 2 in front, I would have had twice as much formed, but this is a 1-to-1 reaction. I don't know what that amount is yet, but eventually I'm going to reach equilibrium. I will change it enough that I do reach equilibrium. So at equilibrium, still not concerned about the ions, but my concentration of carbon monoxide, its pressure, must be 560 minus X. And carbon dioxide must be 113 plus X. Those would be my new pressures. Well, if I'm at equilibrium, then those must equal Kp. That the pressure of my CO2 divided by the pressure of my CO, well, that's going to be 113 plus X divided by 560 minus X. We were given Kp, it was 0.259. So we can rearrange. Let's multiply that up. 113 plus X must equal 560 times 0.259, or 145, negative X times 0.259, so minus 0.259X. We still don't know what X is yet, but we do know that the change on top and bottom by X must bring it to our equilibrium constant, which was 0.259. Rearranging this, I will minus 113. I will add 0.259x to both sides. We'll find that 1.259x must be equal to 32. 145 minus 113. Divide by 1.259, divide by 1.259. X must be equal to 25.45. The only value that if I removed from 560 and added 213, that when I divided them would give me a ratio of 0.259, is this. X must be 25.45, which means my CO, well, we said it was 560 minus X. So 560 minus 25.45. For my CO2, that'd be 113 plus 25.45. So at equilibrium, what are my actual pressures? Well, for CO, the pressure of CO then is going to equal 534.55. The pressure of CO2 will be 138.45. To check, 138.45 divided by 534.55. Do that division, and 0.259 is what you get. So these will be the concentrations that we will have when we reach equilibrium. Indeed, we see that, well, that's a greater amount of CO2. We had not finished the reaction, as we found earlier in part A. And that's less carbon monoxide. We needed to use up more starting material, which again is in line with what we found in part A. And so we used the Q value relative to the Kp to determine which direction our reaction was going to proceed. We then used a nice table to say, for my present amounts, which one's going to decrease, which one's going to increase, so that at equilibrium, it's going to be my present amount adjusted by that change. Whether that's a plus or a minus depends on which direction we're going, but they're going to alter by some amount. In this case, it was an equal amount since they're a 1-to-1 chemical change. Use those changes and the starting values as the concentration at equilibrium. We can plug them into the mass action expression at equilibrium being equal to K. rearrange, solve for x. Use that to find the actual final values of our materials. This has the unfortunate effect of meaning that there's an equilibrium. Not all of the iron oxide has really given up its oxygen. This method as is would not purify our iron all the way. We have modern tricks for this. We don't actually let things reach equilibrium. We'll discuss more about forcing a reaction to go to completion with Le Chatelier's principle more in later videos. But if you continue to stream carbon monoxide over the iron and blow the gas out the outlet, you don't allow CO2 to build up. And so the fresh carbon monoxide never sees any CO2 around, and it continues to drive the reaction towards products. If you have a sealed container where you allow it to reach equilibrium, well, then you'd never actually get all of your iron converted, because there'd always be some CO2 reacting to deposit an oxygen back. And we can figure out just what those concentrations of carbon dioxide would be relative to carbon monoxide using this ice table method. This is a method we will see many more times.